Hello, everyone. First of all, thanks to Ben and Yaga for the invitation to give this talk, and thanks to everyone who's listening. For all of those who don't know me, I'm Dan. I'm a postdoc at Cornell University at the Department of Mechanical and Aerospace Engineering. And in my talk today, I'd like to give a broad overview of what's our knowledge of the various interactions between sulfate geoengineering and clouds of all types, why it's important to understand and model in climate model these interactions, and possibly what are the steps that we should take moving forward to improve our knowledge in this area. The first question that we can ask is, why would we care so much about these interactions? And the answer is because clouds are a fundamental part of the energy budget of our planet. They reflect an important part of the incoming solar radiation, almost 20%, but also, mainly when they are in the form of upper tropospheric ice clouds, they trap part of the outgoing planetary radiation. So they have both a cooling and a warming effect. But overall, as these figures from the AR5 IPCC report show, their net effect cools the planet by a considerable amount. In the case of simulating sulfate geoengineering to cool the planet, on the other hand, we generally see from climate model simulations that it takes around a 1% reduction in incoming solar radiation to globally cool the planet by 1 degree. And of course, this will depend on many factors: size of the sulfate particles, interaction with other greenhouse gases, water vapor, surface feedbacks, locations of injection. But broadly, this is a consistent result. And so, while this is clearly an important part of the energy budget, it is not as big as the global effect that you would get in radiative forcing from clouds. So, if the interactions between this geoengineering method and cloud is important, we can expect it will affect the efficiency and maybe even the feasibility of deploying sulfate aerosols to cool the planet. Overall, we can summarize how sulfate geoengineering would affect clouds in three possible pathways. Of course, we have our sulfate particles, and they reflect part of the incoming solar radiation, and that produces a surface cooling. That's their main goal. And these already would change some of the conditions. It would reduce air moisture, for instance, or it would change the way in which masses of air are transported, depending on how this cooling happens. But the presence of the aerosols would also locally warm the stratosphere because the particles absorb part of the long-wave radiation. And this would, for instance, further change vertical temperature gradients, and it would change stratospheric circulation. And finally, we can expect these particles to, at one point, settle down from the stratosphere to the troposphere, thus maybe interacting with already present condensation nuclei, other than also warming the upper troposphere. And of course, all of the things that I mentioned would affect different types of clouds, formed through different processes in different ways. So one of the interactions that has been a bit more studied in the past has been that between sulfate geoengineering and upper tropospheric ice clouds, as they trap a considerable amount of planetary radiation and have thus a net warming effect on the climate. Other than that, the way in which we represent them in climate model is that their formation is directly dependent on vertical atmospheric stability that will clearly be affected by sulfate geoengineering. So the way in which water vapor that is necessary for the formation of the ice crystal is transported to the mostly dry upper troposphere, where temperatures are cold enough to form the crystal, is mostly through local turbulent ascent of air. Now, clearly, climate models don't have the necessary resolution to simulate these local changes. So generally, in climate model, this is treated by tying this local ascent to the turbulent kinetic energy that is a function of the vertical temperature gradient. So, when we warm the stratosphere and cool the surface, compared to a case with a cold stratosphere and a warmer surface, we have a less steep vertical temperature gradient, and thus we have less occasions for water vapor to reach the upper troposphere. Thus we might end up having less ice cloud formation, especially at low latitudes, that could thus trap less planetary radiation and contribute to cooling the planet. And in the models where this has been studied, that all use a similar parameterization as I just described, this effect kind of consistently represent a further radiative forcing that is around 10% of the direct one from the surface particles. So how confident are we in this result? Well, it mainly depends on the strength of our assumptions. First, we have to assume that the parameterization that we're using for the local vertical velocities is correct in most of the upper troposphere. And we're not sure of that. We know it's correct very close to the tropopause, and we assume it just is the same further below. But in order for what we said to work, we must also assume that homogeneous freezing, so freezing happening on sulfate-coated liquid particles, is a preponderant process compared to heterogeneous freezing, so on solid, mostly dust, mineral particles, that require less relative humidity and warmer temperatures to happen, and so would not be as affected as homogeneous freezing, as I explained. And last, we also have to assume that the sulfate particles settling down in the troposphere would not affect these freezing processes. And for that, we know a little bit that in the troposphere, there is already a large presence of sulfate aerosol. So an increase that seems big from the stratospheric point of view, where there's usually no sulfate, but is not as big when you consider the baseline tropospheric sulfate load, doesn't change things much. And also, lastly, it is generally also much smaller sulfate particles, usually in the Aitken mode, that freeze and produce the ice crystal in homogeneous freezing, whereas the particles produced by sulfate geoengineering are usually much, much bigger than that. So, I started out with high clouds because those are the ones that can, in a way, be parameterized in a simple form in climate models. They are less dependent on the specific sources conditions, and thus have been studied a bit more. But what about other type of clouds? Well, it gets more complicated, of course, but it's still important to understand what might happen. So one example of a paper analyzing this is the one I'm showing now, where they analyze what would happen to clouds in a very simple, highly idealized scenario, where a 4 times CO2 increase is matched by a reduction in the solar constant, so just turning down the sun, to restore global mean temperatures. The first thing to notice is, unlike what I just said, all models except 2 actually show an increase in high clouds, but this is normal since there's no stratospheric warming and is basically just the cooling from the solar reduction going up to the upper troposphere and increasing ice nucleation. But this also highlights how different the results can be if just one important part of the physics is missing from our simulations. But anyway, now let's focus on lower clouds. So in general, all models see a similar reductions in cloud coverage. But what causes this observed reduction that is so consistent across models? Well, as they state, without additional experiments varying potential drivers of cloud changes, it is difficult to prove definitely the causes for the changes in cloud fraction. And that is probably one of the biggest challenges in understanding these changes. But they do still offer some insight on where these changes might come from. In particular, for changes in low cloud fraction over the ocean, they identify a decrease in lower tropospheric stability, which is the potential temperature difference between 700 hectopascal and the surface, and also a decrease in estimated inversion strength, which is a metric of the temperature inversion at the top of the marine boundary layer. They also suggest that for medium clouds near the tropics, shifts in the ITCZ that are produced by both the effect of climate change and of a broad reduction in the solar constant might be a cause. And finally, they also suggest that for low clouds over land, changes in plant physiology, mostly due to CO2 changes, could also produce these changes. So to separate some of the observed effects, I'll show you some results from simulation I worked on during the last year that might shed some light on some of the various mechanisms at play. It all started out with the simulation most of you might know as GLENS, that were performed with CSM1 Wacom, and whose aim was to use SO2 injection not only to restore global mean temperatures to early century levels, but also to restore interhemispheric and equator to pole temperature gradients by injecting at different locations. And compared to a strategy whose only aim was to reduce global mean temperature, it has been already shown how this allows for a further reduction in some of the side effects of sulfate geoengineering. To these 2 sets of simulations, we have now added 3 further sets of simulation with the same model. One that simply turns down the sun, as in the G1 experiments that I showed before, to manage global mean temperature. that respond to the question what are we missing if we turn down the sun as a proxy for a more complex stratospheric sulfate strategy. Then we have another set that turns down the sun depending on the latitude, exactly as it would happen with the sulfate injection, to understand better what would happen in this case. And finally, we have a final set that turns down the sun the same way, but with the stratospheric heating from the aerosols imposed on top, where we can better identify the role of stratospheric heating, for instance. What happens to clouds in these cases? Comparing pairs of sets, we can get a better idea where these changes might be coming from. So for the turn down the sun case, we see results that are broadly consistent with what I showed before. But it turns out that by managing also the other temperature gradients, most of these changes can be reduced, indicating that large-scale differences in energy transport are also a key component in understanding cloud changes. And especially for high clouds, however, the inclusion of the stratospheric heating is also crucial to see some of these changes, especially the reduction again. And finally, here it appears as if the presence itself of the aerosols also produces very important changes in the clouds. For low clouds, it appears like the changes that we see are more directly tied to the state of the surface climate. So, for instance, the large reduction over the North Atlantic kind of coincides perfectly with the change in the Atlantic meridional overturning circulation that we see. But more in general, we can see how the changes in sea surface temperature drive some of these changes that we observe in low clouds. For medium clouds, we can note how the changes that are observed in the turn down the sun case are not at all reproduced in the case that manages other temperature gradient, confirming that even when we are turning down the sun, most of the changes that we observe in medium clouds in models might be due to large-scale changes in the circulation. And however, we can also observe how the inclusion of the stratospheric heating and of the aerosols themselves changes things considerably. Especially, we can see at high clouds the big change between the sulfate geoengineering cases and the cases that just turn down the sun. These might be due to a lot of factors that I've not investigated yet, but for instance, one possibility is that that's due to seasonal changes in insolation that are not reproduced without the aerosols. Finally, for high clouds, while the inclusion of the stratospheric heating reproduced quite well the reduction that is observed in other models and that I explained before, in sulfate geoengineering cases, there is a far larger reduction that can only be due to the presence of the aerosols themselves. So, however, if you remember what I said before, these would kind of oppose the conclusion of previous studies stating that changes in high clouds are not due or should not be due to the increase in sulfate particles. So, if these changes that are observed in CSM1 are real, that kind of would change our understanding of most of these changes. It appears to be, however, that these changes in high clouds that we observed are not due to a physical change in the system, but they might actually highlight a potential limitation of using a model approach to microphysics when simulating sulfate geoengineering in climate models, since it appears that in the troposphere, the presence of coarse mode sulfate appears to be modifying the concentration of other species of particles, and thus in the case of ice cloud, it kind of shifts the heterogeneous and homogeneous freezing ratio. So just to conclude, we should pay definitely more attention to how sulfate geoengineering might modify cloud cover and how it might change different kinds of clouds in different ways. Some of these changes, they might be due to physical differences, whereas some others might be more due to the specific strategy of geoengineering use. And by strategy, I mean what we want geoengineering to do. Is it just to restore global mean temperature? What is the baseline scenario we're using? How much we want to reduce temperature? Do we want to also manage other temperature gradients? Where do we inject? How much we inject? And lastly, and the thing that I think it's also very interesting, is that exploring some of these changes that we see in climate models can also highlight some of the limitations of our current parameterizations in various areas of our climate models. Thank you for your attention.